you everyone for coming. First of all, can I check that you can hear me at the back?
Yes.
Yeah.
Yes, fantastic. So yes, I'm Amy Rankine. I am a third-year PhD student here at the Institute of Astronomy, and I work on active galactic nuclei. So that's what I want to talk to you about today. I'll run through what they are to begin with, or I will often say AGN or quasar instead of active galactic nucleus. It's quite a mouthful. I'll then give you about the history of how they were discovered, and then I'll go on to how some newer research into how we think they affect their galaxy that they sit in, and basically why they're important, why we should be thinking about them. Then at the end, I'll talk about some of my research on some of the brightest of these objects, so quasars, and I'll talk about their winds as well. So first, what is an active galactic nucleus, or AGN? So there are hundreds of millions, hundreds of billions of galaxies in our universe, just like our own. At the centre of every one, we think that there is a supermassive black hole. And some of these black holes are accreting a lot of material, so are swallowing a lot of material up from the dense central regions that surround these black holes. And this produces a lot of light, and it's this light that we see in the sky, and that makes these some of the brightest objects that we have in our universe. So this is kind of a zoomed in image of an artist's impression of an AGN. So in the center we have our black hole. Surrounding this we have an accretion disk that where all the gas is swirling round and then falls into the black hole. And as it does this, it's emitting a lot of radiation as it's swirling around here. This radiation can push on some of this gas and can produce these nice winds that we can observe. Some AGN also have jets, and what these jets are is one of the questions that people are trying to answer today. We know that there's some hot plasma that is being ejected from somewhere near the black hole, and it's extremely fast and extremely powerful, and it can really leave the galaxy, but that we don't know very much about them yet. And then surrounding all of this, we have a dusty torus. So this is kind of a donut structure that surrounds all of this, and it can make it really difficult to observe some of these objects that are in the sky. Because it'd be like, they're so dusty, it'd be like looking through a dust storm and you just can't see very much. So they can both, some people spend all their life studying just the dusty bit, but for lots of us, they're just a nuisance. It wouldn't be an astronomy talk if I didn't show you some pretty pictures. So this is one example of an AGN, and we can see these nice jets that are coming out of the galaxy. So this is the whole galaxy here. So you can see the extent that these jets are escaping onto. This is another galaxy, and it looks quite boring in this image. So this is the optical image. This is what we'd see with our eyes. But if we look at it in the radio, we can see these really lovely jets, these really nice radio jets that are, as I said, coming all the way out of the galaxy. And if you look closely, it looks almost bubble-like. There are these bubble-like structures, which makes us think that these jets are happening periodically. There's an episodic behavior to them. So they're turning off, and then they're turning on, which is producing these nice bubble structures. But these pretty pictures have only been possible in the last few decades as a result of lots of the new technologies that we have today. Historically, AGN were somewhat of a mystery and the source of much confusion and debate. So this here is one of the first papers that kind of puzzled over what these objects were. This one? Oh, what they've done. Oh, it's there. Oh, yeah. Okay. This team at our radio observatory, they were looking at the sky and the radio in the 1960s, And they found lots of bright radio sources, and then they went ahead and looked at the optical images, see what they looked like, and they looked like stars. And this was confusing. We had these star-like objects with very strong radio sources. So this is one of the first ones that was discovered. It looks like a star. This is a newer image. So in the background of this image, you can also see another one of these jets. The result of one of these jets that was coming off it. But they just look like stars, and this was confusing. And it wasn't until a few years later when Martin Schmidt came along and was able to look at the optical spectra of this object. So the spectrum. This is just as a prism can split light, we can use spectrographs to split the astronomical light from objects in a telescope to determine different properties about the object that we're looking at. So we've had all this light, we split it into the different wavelengths of light, and we can look at how much light is at different wavelengths. And so you can tell different things about these objects from their spectra. So the shape can tell you something about the temperature. The emission line, so these peaks here, can tell you about what gas is producing this light. So just as if you were to take a helium lamp and you were to split the light using a prism, you could see that this was made up of helium by what emission what different wavelengths you could split this light up into. So Martin Schmidt used these emission lines in the spectra to determine how far away this object was. So he used the fact that the universe is expanding, so everything's moving away from us. And as everything moves away, everything's moving faster. And because it's moving away from us, the light is expanding. So just as when a fast car goes past you, you can hear the noise that the car makes changes as it whizzes past you. This is because it's moving towards you and then it's moving away from you. Light does the same, just on a much smaller scale. So he used this to see that if So the light is being Doppler shifted, it's being stretched to longer wavelengths, and we call this redshift. So if this line here is at this wavelength, then it's 8 billion years ago or away. If it's redder still, then it's even further away, and if it's even redder still, it's even further away. And so Schmidt used this when he was looking at the spectrum of this star-like object, and he noticed that he was looking at the hydrogen series. So hydrogen produces these lines, but they were all shifted to very high wavelengths, which told him that this object is so much further away than any star could be for it to shine this bright. And so this was the paper that was produced because of it. So a star-like object with large redshift. And the name quasi-stellar object, or quasar, was born. So I've spoken a bit about what these AGN are, but it's also interesting to discuss what impact they have on the galaxies that they are sitting in. And we call this process feedback. So the question that scientists want to answer is, can these outflows, can these winds, these jets, interact with the galaxy, maybe heat the gas up so that it can't form stars anymore, or even completely remove the gas from the galaxy to prevent its star formation, to prevent it from forming stars. So when we can do this with simulations, so this is a simulation from another PhD student here, and she was looking at the effect of AGN on a disk. So the disk is in here, and we're looking at, on the left we've got the simulation without an AGN, and on the right with an AGN. And the effect of the AGN is quite staggering. So we can see this in simulations, but can we see this in observations? So one of the techniques that's been useful for this is interferometry. So this is a technique where you take lots of different dishes or telescopes, many here, and each of them is looking at the same object. And you can then combine those images that each telescope is producing to produce really nice high-resolution images for objects. So this is what this team did here. So on the right, we're looking at the optical image of this cluster. So we've got a galaxy in the center here. The center, this cross is where the AGN is, so the center of the galaxy is here. And on the left, what we're looking at is the molecular gas. So this is the gas that can form the stars. And what we can see is that there's lots and lots of molecular gas in the center. But we've also got these nice tendrils that are coming out of the galaxy to quite far away from the middle of it. So this is like this bit here and this bit here. And they're kind of curving quite nicely around these dashed lines, if you can see them here. And these dashed lines are outlining radio bubbles. So these are bubbles that have been produced by the jets blasting out into the rest of the galaxy. And we can see quite nicely that this molecular gas, so the gas that could at some point form stars, is clinging quite nicely to the radio bubbles, which is telling us that there's a really strong connection between the AGN at the center of the galaxy and all of its jets and the gas that's sitting in the galaxy that could hopefully form stars. But the question is still, is this gas going to be blown completely out? Is it being compressed so that it could form stars, or is it going to be too hot? And these are still questions that people are trying to answer today. So now I want to talk about some of my research. Obtaining high-resolution images of every quasar would take a very long time and it'd be extremely expensive, particularly for lots of the, how many have we got? I think it's hundreds of thousands of quasars that we have today. This is an example of one here. This is the image that we have of this galaxy, this quasar. So one of the techniques we can use is spectrometry. So that's what I've already introduced with the spectra. So we can look at the spectra of these objects to decide what is going on in these objects. So this is what I've been doing in my project. And in particular, astronomers like to do one thing at a time. Some astronomers have used the emission line, the emission from these quasars. Other people have looked at what light has been absorbed by these, by some of the other things that are going on in these quasars. But I've tried to combine these two paths to get a proper handle on what is going on in these with their winds. So in particular, I am looking at the carbon-4 line. So this is this nice line here. So this is triply ionized carbon. You might know it better as carbon-3+. So this is a carbon atom. Carbon has 6 electrons. A photon has come along, a packet of light has come along and thrown out 3 of its electrons. So this is why it's carbon-3+, or carbon-4 if you're an astronomer, because astronomers like to name things weirdly. So to produce this carbon-4, we know that we need lots of really high energy photons. And so to get where we can get these high energy photons from the central regions of the accretion disk and the base of any wind that's produced. So we can use this carbon-4 line to look at what's happening with their winds and what's the interaction between the wind and the disk. And we call these models the disk-wind models. The idea that quasars have disks and winds is widely accepted, but there are still lots of questions to be answered. What shape is the wind? quite straight or quite curved? Is it clumpy or smooth? What drives the wind? Is it this radiation pressure, so photons pushing on the gas, is that what's pushing the wind out? Or is it magnetic fields? All of these things vary across all the different types of these models. So one of the ways that I'm trying to answer this is looking at the different outflow signatures. So the first one is in emission. So this is a nice carbon-4 line again. And just as things that are moving away from us look redder, things that are moving towards us look bluer. So if we have our wind here and it's moving towards us, it looks bluer, so it's shifted to the lower wavelengths. So before, it's quite symmetric, and then it's blue shifted, and it's all kind of skewed to that side now. So we can use that to look at how strong these outflows are. So the more skewed it is, the stronger the outflow is. The other signature is absorption. So if you've got gas here that's emitting light, it's then passing through a clump or a cloud, and so this is what the emission first looks like. You've got the carbon-4 line again. It's passed through a cloud, and the cloud then absorbs a lot of the light. And we see this absorption in about 40% of the quasar spectra. And we call these quasars broad absorption line quasars. So the question that I want to answer is, why do we only see this absorption in some spectra? Why isn't this something that we see everywhere? So in essence, how do these BALs fit into the disk wind model? There are two camps of people. Some think it's orientation. So every quasar is a BAL quasar. If they were all orientated in the sky the same way, and if all of them, we could see them all down this way, then maybe they'd all be BAL quasars. The other option is evolution. So at some point in every quasar's lifetime, they were BAL quasars, and they've got all of this absorbing gas that's making it a BAL quasar. But then, for some reason, don't know why this would be either. For some reason, all of this gas is expelled, and then it becomes a normal quasar. We don't have these absorption lines. So we can look at the emission signatures and the outflow signatures and the absorption signatures to try to get a handle on that. So if we first look at emission, so we've got spectra. So at the top we've got the normal quasars, and at the bottom you can see we've got these nice deep absorption lines. And we've got very weak outflows here, because the lines are very symmetric. And then we're more skewed as we go across here, so we've got strong outflows. And in both the BAL quasars and the non-BAL quasars, the normal quasars, we can see that the emission lines are extremely similar. So we've got very similar emission lines for both BALs and non-BALs. So that's kind of interesting. I'll come back to why in a moment. But we can also look at the absorption outflow speed. So what I've got here is the same. So we've got the amount of carbon-4 gas here, and against how strong the emission outflow is. So how skewed is that emission line? And things down here, these are the spectra that have got the really strong outflows. And on this color bar here, the bluer the line here, the faster the broad absorption line outflow is. And so it's spectra down here that have the fastest emission lines, the fastest emission outflows, and the fastest absorption line outflows. So there's a strong connection between these two absorption signatures. And this is something that people hadn't really seen before, because, as I said, people only looked at the emission or the outflow, or the absorption, sorry. But we can also get an idea of whether it's evolution or orientation here. Spoiler, don't think it's either. Because, so if it was evolution, we would expect all of the broad absorption lines to be down here with these strong outflows. Because remember, it's all of the gases being pushed out at one time. So we would expect them all to have really strong outflows. But we don't see that. We've got broad absorption line quasars all over this space with really weak emission outflows. And then on the other hand, if it was orientation, we would expect all of these all of these broad absorption line quasars to have really weak emission, because we would be seeing them like just above the obscuring torus, so just over that dust that I mentioned in the torus. And we don't see that either. Again, we've got really strong emission in some of these spectra. So we don't think it's evolution, and we don't think it's orientation. So it looks like we need a new model to explain these broad absorption line quasars with these non-broad absorption line quasars. Maybe it's got something to do with having a really wide wind, and the only difference is whether or not you're looking down between these clouds that can absorb it in the first place. But that, I'm not sure either yet. So I'll leave it there. Thank you.